Did you know Mona Lisa doesn't have any eyebrows? And there are eyebrows, but he had painted over them because he was still working on this. He worked on this for years and he died, and he never put the eyebrows back in. Did you know he was the first one to ever paint the background with lower resolution than the foreground? Everyone before him would paint everything in high resolution, which is not at all what real life is. But anyway, who cares? Who cares? I don't care about Mona Lisa. I mean, she doesn't affect my day, right? If something is aesthetically pleasing, that's good enough. Nanomachines are just interesting. So whether they have a function or not is irrelevant. It's like Mona Lisa. Last time we were talking about this flashing to just heat things up and distill them out. And I mentioned that we got this DARPA project, and I'm going to show you the results of this project which we were able to deliver on in 15 months. We were given 18 months of funding. We were able to deliver it in 15 months. And I'll explain to you what we're doing. It's taking this up another level. And remember, what it does is it allows us to take waste. I mean, students are really concerned about the future, right? And you should be, because what's the world going to be like? Are we going to pollute the whole world? But when we can take waste and remove the metals from it, because remember, metals should be theoretically infinitely recyclable. And so we shouldn't have to do so much mining if we just can reuse the metals. So flash joule heating under an atmosphere of chlorine. Chlorine is used a lot in the industry, and so it's no problem for them. But what it capitalizes on is the free energy of formation of the metal chloride. And as soon as the metal chloride forms, boom, it just distills out. So let me show you this. So the idea is this. You can take a metal oxide and you can react it with chlorine gas and form the metal chloride. All right? Or if the metal oxide won't react directly with chlorine, what you can do is you can add carbon to it, and that will, the carbon will reduce the metal oxide to either a lower valent metal oxide or a metal, just a metal zero, just a metallic system. That will then react with the chlorine to form the metal chloride. So you have these two possible routes. So one is a chlorination, the other is what's called a carbochlorination reaction. To make the metal chloride. Well, why would we want to make the metal chloride? Well, look at this. Iron oxide boils at 3,400 degrees, but an iron metal at 2,800. Again, still very high. But iron chloride is at 315, so a much more accessible temperature. Titanium oxide, almost 3,000. Titanium metal, which is titanium zero, is 3,200, 3,300 degrees. Titanium chloride, tetrachloride, 136. So you see how much easier it would be to distill these away. And so we built a system that has a carbon layer between two electrodes, a carbon layer between two electrodes. You put your material here that you want to separate, you flow in chlorine. It's going to give out oxygen as the metal oxide converts to the metal chloride, and the metal chloride would evaporate. What you can do is you can look at the temperature at which these metals would react and begin to look at it in this way. So it turns out we built this 1-inch tube furnace system. There's a 1-inch tube here. Here's the chlorine cylinder that's going to end up feeding into this. So we built this in our lab. This is in a hood. And this is a 1-inch tube here. Then we had to enlarge it, because as we get up to a larger scale, we had to enlarge it. So this is now a 2-inch tube here, 2-inch tube. And then we had to go to a 3-inch tube and make these fittings at the ends, and still the chlorine gas being able to flow in. And this is now as long as, so the hood is about 6 feet long, and this fills up just about the whole hood. So it shows you that what happens here. If you do not believe in the physical resurrection of Jesus Christ, send me an email, tour@drjamestour.org, and we will get together, and I will share with you about why I embrace the resurrection of Jesus. And so we developed this 1 inch, 2 inch, and 3 inch. And actually the tubing is still sold in inch designation. So you buy a 1 inch inner diameter, 1 inch outer diameter, 2 inch, and 3 inch. And so it's still sold like that. And that's why we're using inches here. All right, so what we had to do is we had to take real waste and get the metals out of it. So remember, one of the metals that they wanted us to get was indium, and we had to demonstrate it on real waste. So we bought indium tin oxide. So indium tin oxide is what's on the surface of your phone. When your finger slides along this, if this were just glass, it wouldn't be conductive. But the glass is coated with indium tin oxide. And we've discussed this a little bit before when we were making graphene and making films out of that, conductive coatings out of that. And that lowers the transparency of the glass by about 10%. But you don't notice it, but if that glass from the iPhone would be put on a piece of white paper versus a piece of glass without the ITO coating, you would notice the difference. You can see 10% of absorbance in the visible region. So we took this, we got some plastic that has indium tin oxide on it, and what we did is we just calcined this, which means you just heat it up in air. That burns away all the plastic and leaves just the metals. All right, so the metals just end up in here. And there's actually more gold in here than there is indium. And so we'll go after the gold as well. So it's gold and indium, and then a lot less of tin, manganese, chromium, and so you just antimony, and you just go through and you get fewer and fewer, lower and lower amount of elements. And then what you can do is you can plot. There are calculations that you can do, and these are just standard thermodynamic programs that you can buy, so you don't have to write the program. You can buy a program that'll do this, that will tell you at what temperature this should react with chlorine. When the delta G is less than 0, the reaction is going to be spontaneous. And so you see that tin oxide would react with chlorine at somewhere around 630 degrees, right here. Gold is actually going to react at somewhere around 250 degrees, below 250. It's going to act. This says that the gold should end up reacting, but it really is not going to end up reacting directly. And the problem is that there's no stable gold chloride at atmospheric temperature and atmospheric pressure. So gold, we're going to have to go after it in another way. But anyway, we can get the indium out. As long as we just heat it quickly to this region, only indium should come out. The manganese shouldn't come out until you get much higher, up here. So hopefully we can just heat it up to right in this region and pull out the indium. So we want to take this mixture. It has indium oxide, tin oxide, gold, manganese oxide, chromium, and do the chlorination. And we would get indium chloride, and we would get these other compounds would remain as the oxides. The gold would remain as the gold metal. And then as soon as that indium chloride forms, we should be at a temperature where it would immediately distill out. And then you could take this residue, you could do the chlorination at over 1240. So remember, if you go over 1240, up in here, you should get this, and this. It should get all of those other ones. So all of those other ones will form the chlorides. It turns out the chromium, though, doesn't, because you see, chromium never goes less than 0. The chromium won't. And so the gold remains as gold metal, the chromium remains as the chromium oxide, and here you distill out now the tin chloride, the manganese chloride, and you're left with this in the residue. But if we go back to the original chart here, the amount of chromium is actually very low. And so what you can see here is the raw waste is mostly plastic. Mostly plastic. The metals are just a small amount of metals relative to the plastic. And that's the way the industry wants it. The metals are the things that are much more expensive than the plastic. Then you calcine it, which means you heat it up in air, so the plastic's all gone, so it's mostly gold. Then you have some tin, and there's the indium. So then if we do the flashing at 100 volts, you get this much higher amount of indium. But if you do it at 105 volts, we drive all of this to completion, and we get almost all indium here. There's going to be a little bit of other things in there. And so it's at 105 volts, we're going to get up to about 95% purity. And then on the yield, it's going to be 92%. So at 105 volts of flashing, 95% purity, 92% yield. Considering that 99% of the mass was polymer, a productivity rate is 180 grams per hour of this electronic waste that could be recycled. Then we want to go after the gold. So at 105 volts, we achieved gold at about 80% purity. So we got gold at 80% purity. And in order to further improve the gold, the chlorination temperature was increased to over 1240 to remove the tin chloride and the manganese chloride to leave gold. So gold, we could get 96% purity, 82% yield after the second chlorination by flash Joule heating. Now this is gallium waste. Gallium is used in LEDs, light emitting diodes. And it turns out it's a very, very small amount of gallium. Where the gallium waste really is in the periphery of when they're making the electronics. And this is the periphery of when they're making the electronics. And this is my student took a picture of this, so you can see his iPhone right here as it's reflecting in this gold coating over the top. So as he took this picture for us of the wafer. So the wafer has gold, the wafer has silicon oxide, silver, and the gallium nitride. And then there's a photoresist, and then the silicon substrate. Most of the weight is in the silicon wafer. There's a little bit in the metals that are there. So after you remove this from the silicon wafer, so now you're pulling off these metals off the top, you can see the gallium, the silicon, silver, and gold. And then if you look at the thermodynamic chart, you can see that both silver and gallium nitride should spontaneously come off under the chlorination reaction at any temperature. It doesn't matter the temperature, they're always less than 0. But if you look at the boiling point, gallium chloride boils much more easily than silver chloride. So silver doesn't boil until 1500 degrees, silver chloride. So we should be able to separate this just based on a very simple separation evaporation. So you take the LED waste, you do this electrothermal chlorination, and that's going to make silver chloride and gallium chloride. Gallium chloride evaporates out, and you have silver, gold, and silicon oxide in the residue. So this is what it looks like. Here's the raw materials. And then here's the evaporated phase over the top, and here's the residue. So here's the raw waste, substrate you get rid of, and here it is with gallium is what we want to go after. When we brought it up to that flash temperature, we get mostly gallium with a little bit of other impurities. So we could get gallium at 97.5% purity and 86.5% yield. Again, meeting the DARPA milestones. So DARPA puts upon you these different milestones. Then we got tantalum capacitor waste. All of this waste we get from eBay. It looks like sort of like little pieces of candy, these tantalum capacitors. So you grind it up, and then you calcine it. That'll burn away the plastic, and you get the tantalum capacitor. You see tantalum there, and then when you oxidize it, you burn away the plastic. You get tantalum. You get the tantalum oxide. Just a quick reminder, this organization is run totally by volunteers, but we do have to pay for the production work. If you could help us out by going to give.jesusandscience.org, we'd appreciate it, or you can click in the description box below. If you can't give, we certainly understand, but please just give us a thumbs up and click subscribe. Thank you. So it's mostly silicon, but it's still a high percentage, like 37% of it, 37.79% of that residue is going to be now tantalum. And so here's the thermodynamic chart here. So consider this. if you do the direct chlorination, what you'll do is you chlorinate the iron and the nickel and the manganese and the copper. So in this region, you're going to chlorinate all of these, right? Because all of these are below zero. And that's going to leave silicon and tantalum. Silicon and tantalum are not going to react with chlorine at any temperature. However, if you do the carbochlorination, so now you add the carbon to it to reduce these, then the reactions can go. So if you do a carbochlorination, both of them are going to be spontaneous over the entire temperature range. So how are you going to separate them? Well, what you can do is you can take silicon oxide and react it with carbon and chlorine and see how fast it reacts. So you go through what's called an Arrhenius equation, and you can just, and so this is not something you can calculate, this is something you have to determine. So we go in the lab and we determine this, and it turns out the activation energy to get silicon to react, although thermodynamically it's favorable, meaning that the product is more stable than the starting material in the sense this is thermodynamically driven, but you have to look at how high is the barrier to go over to get this. So this is 53 kilojoules per mole for silicon, 31 kilojoules per mole for tantalum. So we should be able to do this, hit this barrier before this one ever activates. And so what we'll be able to do is separate out the tantalum from the silicon, because the activation energy to make the chloride from the carbochlorination is in our favor. So you take the tantalum capacitor and we do the direct chlorination. That gets rid of all of these metals, come out in the evaporated phase, and then you just have silicon oxide and tantalum oxide, and then you do the carbochlorination. You get the tantalum chloride. Silicon oxide has not reacted. This goes in the residue. This evaporates out. When we expose it to air, it goes back to tantalum oxide. And so you can see that in the first step, all those other metals came out. In the second step, just the tantalum chloride comes out, which then forms tantalum oxide. So tantalum was 95% purity, 86% yield, and so here's the productivity. So what you do is you supply to DARPA this. They tell you what you have to get. We had milestones that we put upon ourselves. This was the milestones for DARPA. They wanted at least 95% purity from all of those systems and at least 70% yield, and they wanted 40 grams per hour productivity. And so we were able to check off every box here and get the productivity that they wanted and the purity that they wanted. And so that's sort of how you do this. So we can extend this now. This method, remember we talked about bauxite residue or red mud. The big problem is removing iron from the red mud. The reason this looks red is because it has iron in it. Hematite is a form of iron oxide, and it's red. That's why it's called red mud. It's a bauxite residue, so you're taking aluminum oxide, and then which is bauxite, and then you reduce the aluminum with that sacrificial electrode with its power plant, but you're left over with some aluminum that's very hard to separate from iron. So this is the residue after they've gone through and done all this. Yeah, it has like 23% aluminum, but it has like 45% iron. And because this is so impure, this is what's called their tailings. They can't use this. This is unusable. So all of this just piles up as that red stuff all over and just contaminates the earth. This is a toxic waste now, and it just contaminates the earth. But what we can do is we look at all the different elements in here. We look at the thermodynamic plot, and what you can see is the main elements are iron, aluminum, silicon, then sodium, titanium, magnesium, nickel, tiny bit of copper, tiny bit of rare earth elements. Among them, all of these can be chlorinated at 1450 degrees. So at 1450 degrees right here, all of these can be chlorinated. This one, these two, there's two under here, calcium and nickel under here, and this one. All of these are going to be chlorinated, and this one. So that's how the separation will go. Now, how does the industry normally remove the iron from these tailings? Here's what they have to go through. So this is state of the art. this is what's done now, is that you have this red mud, they mix it with lime, they mix it with a reductant, and they mix it with sodium carbonate. They put it in a mixer, then they roast this. So they put this in an oven, and that's a lot of energy. And then it gets crushed in a mill, and then they do water leaching to recover the aluminum, so they recover the iron with a magnetic separator. And then they go through this hydrolysis step. So all of these steps are buried now in this one step. So you just do the red mud, you do the chlorination reaction. In the evaporated phase, you get this. In the residue, you get these three systems. This is very easy for them to now put in their normal separations and get the aluminum out, because you've gotten the iron out. That was the big impurity to get out. So you see how many steps. This is what the world goes through now. All they have to go through is just chlorine and a reactor, and you'll purify this right out. And so you can see that at 15 amps, it was sufficient to reduce the iron. This was 46 weight percent to 2 weight percent. And this is the spectra that showed that you can get these out. But the bottom line is here. This is the red mud. This is all the iron that's in the red mud. After you flash it, say at 10 amps or at 15 amps, you bring it back down to about 5% iron. So there's only about 5% iron left in this at the end of it. And that's good enough for them to now do the separation. So what we've gone through between last time and this time is we went through, and the other times, we went through a few different methods. Remember when we were growing graphene, you'd put this in a furnace and you'd feed in like a gas and it would grow on a surface. The graphene would grow on copper, say. That took anywhere from minutes to hours to do. That was called CVD. Then we looked at a laser-induced graphene. Remember, that was a laser method. That's forming in microseconds. And what we've just done is we talked about flash joule heating. That's forming from milliseconds to seconds. That's the time frame. And so these are three different methods to do synthesis of these nanometer materials, the nanoscale materials, and how to do these reactions at different time scales. So now we'll discuss nanocars. Why would you want a nanocar? Why would you want a small car? Well, why wouldn't you, right? You know, if you can make something this big, why would you want something that small? So this is 10 to the minus 24 kilograms. This is 280,000 kilograms. If you put a person here, a person would stand about this tall relative to this truck. This is the truck that's used in coal mining. So you see how much material goes on one of these trucks. These trucks are huge. So, you know, a person walks up these steps, sits up here and drives this thing. So it's really not how big your truck is. It's how many trucks have you. If you have a lot of them, you can do a lot. So have you ever, we talked about this before, I think maybe. Fire ants, did we talk about fire ants before? Have you ever experienced fire ants? People, yeah, you have, right? If you're from Texas, you have. You step on a fire ant mound and they all come out. Well, you could have a beautiful lawn, and then the next morning you come out and there's this pile of dirt on the lawn. You're like, where'd that dirt come from? Well, it was fire ants were working underneath the ground, and they were digging tunnels under there, and they had to put the dirt someplace, so they just stacked it up. And you say, well, how did one fire ant do that? It wasn't one fire ant, it was many fire ants. So when you have many entities, they can do a lot. Let me give you another example. We have hemoglobin in our bodies, and each heme within hemoglobin only carries one molecule of oxygen. So how do we survive if only one molecule of oxygen at a time can be carried? It's because we have 10 to the 23rd hemes carrying oxygen. So you get enough of them carrying oxygen, you can do okay. Your cell is crying out for oxygen, and so what happens is the heme delivers it to your cell, and then to detoxify the cell, it pulls out CO2 and protons on the way out. And so you get this detoxification of the cell. And again, each heme is only carrying out one molecule of CO2, but you do okay because you have many of these hemes carrying it. So you see what I mean? If you have 10 to the 23rd of these, you could do some real work. You don't just use one. That's the idea. So why nanomachines? Well, why Mona Lisa? You know, what good is she? I mean, what's the purpose? What work does that do? Did you know Mona Lisa doesn't have any eyebrows? Did you know that? I read that book by Isaacson on Leonardo da Vinci. And there are eyebrows, but he had painted over them because he was still working on this. He worked on this for years, and he died while working on this. It wasn't done. And he never put the eyebrows back in. But it's really a clever painting because the eyes are slightly crooked. You know, one is off a little bit, and that's what gives you the sense, if you stand here or if you stand here, she's still looking at you. I don't know if you have ever seen anybody with a little bit crooked eyes. You don't know if they're looking at you, and you don't know which one to look at. Which eye do I look at? Do you know what I mean? And that's he painted that into this thing. It's extraordinary. Did you know he was the first? He was the first one to ever paint the background with lower resolution than the foreground. Everyone before him would paint everything in high resolution, which is not at all what real life is. What real life is, the things that are up close, you have much higher resolution than the things that are far away. And he was the first. You see these sleeves, how they are? He was the first to do sleeves and curtains like this. They're really hard to paint, apparently. Sleeves, curtains, things like this, because of all the shadows that come in. He was the first to do that. But anyway, who cares? Who cares? I don't care about Mona Lisa. I mean, she doesn't affect my day, right? If something is aesthetically pleasing, that's good enough, all right? Just because and nanocars nanomachines are just interesting. So whether they have a function or not is irrelevant, right? They're just pleasing. It's like Mona Lisa. All right, and if you consider a tree, how was that tree made? Was that tree made by chopping down a much bigger tree and whittling out that tree? No, that tree was made from the bottom up. It wasn't made from the top down. It wasn't taking a larger structure and making that tree. It was made from the bottom up. So, but once you have that tree, you can make a table, right? You can cut down the tree, cut the wood, and make a table. That's top-down construction. That's how people normally build. That's not how nature normally builds. If you go into nature, most things are built from the bottom up, like that tree was made. That tree was made by bringing in certain nutrients, and then cells were constructed, and you got more and more cells, and the tree was built bottom up. That's how nature builds. We generally build from the top down. We take something large, and we cut out tables, things like that. Well, nature went bottom up. These seeds were the progenitors of that tree. Now you could think of just having atoms or carbohydrates, because wood is a carbohydrate, so you could just take carbohydrates and you could use nanomachines to build a tree. Right? You could think about that, right? Why couldn't you build that table? Why couldn't you build that table bottom up? Why couldn't you? Just take wood is just carbohydrates. Or why couldn't you just take these seeds and reprogram the DNA in one of these seeds, so rather than going to that tree, reprogram it so that it goes to the table directly? Wouldn't it? I mean, it's just, you have the code in the DNA, so just restructure the DNA so it makes a table rather than that thing. Why does it make this? Well, because it's coded to make that. What if you coded it to make this? And so this is the way we want to think. We want to think differently. Can we build from the bottom up? And years ago, we had proposed to DARPA to build structures because they wanted to be able to build structures rapidly in remote areas. And we had proposed this method where you would have this little cabin for soldiers, and that would, from the bottom up, the cabin would grow. The cabin would just grow from the bottom up. I thought it was a really interesting proposal. They didn't fund it, but that's their loss. But it could be done. It could be done. So you can build so that things would bottom up, build the structures that you want. But in the future, that's how it might be done. So that in the future, we might build skyscrapers this way. Why can't you just bring in atoms or small molecules and bring in nanomachines and have those nanomachines build these structures from the bottom up? You see? Isn't that interesting? Wouldn't that be good? And you can build all these things from the bottom up. But anyway, you build from the bottom up. I don't think even in your lifetime you're going to see skyscrapers being built from the bottom up in the sense of bringing in small molecules and having nanomachines. But I think in, 200 years, this might be the way you do it. You say, oh, come on, I don't believe that. Well, how do you think all the natural structures were made? All the trees were made. They were all made from the bottom up. What makes you think, or do you believe that those trees were made from the bottom up? I mean, do you? All right, if they can be made. And there are, and you say, well, they grow too slowly. There are some things like bamboo. Bamboo can grow 3 feet tall in a single day. Single day. So that's really fast. 3 feet tall in a single day. That's actually faster than they put up buildings around here. Can you imagine 3 feet tall in a single day, just keep building? And the sophistication in that bamboo, if you look at it at the cellular level, is more than the sophistication in this building. And so there's no reason why we can't. So this is what I want you to think about. Now, how we do it, is another thing. So don't propose this for your invention because you have no idea how it will be done. But it's something to just think about, to just dream about. All right, so here was the synthesis of our first generation nanocar. I mean, we plowed through this. There's a bunch of different steps here. Then you could buy this compound and then do a bromination. You make the ketals, and then you convert the bromos to these solubilizing groups. Then you take off the ketals and you iodinate. And then we did a condensation with this compound, a condensation, pull off the tosylates, and then did a condensation on the other side. So here's the chassis and the axles of what was going to be our first nanocar. It took us not long, a couple of months to make that entire chassis and axles. It took us 6 years to get the wheels on. Why? Well, science is like that. I mean, it just was tough. It was tough to get the wheels on. And so the thing is that research is not for the cowards. I mean, you just got to go in and you just keep throwing graduate students at it. Just keep throwing the soldiers in front of the machine guns. Eventually they'll run out of bullets and you overrun them. And this is what it is. You keep throwing forces at it and you keep going. This is what research is. It's a lot of work. And here where the wheels went on. So there were 4 fullerene wheels on the fully rotating axles with the alkynes. But you know where we got the idea for this? If you look at this, the top and the bottom of this car are the same. The front and the back are the same. And so we got the idea from these little cars that kids have that have the same sort of arrangement. The top and bottom are the same, front and back are the same, so it doesn't matter how it lands on a surface. It's just that this had such poor solubility, it couldn't be characterized well. Even though it had these solubilizing chains, still this was so rigid it could not be easily characterized. But that was our Generation 1 car, the G1 Nanocar. Then we made the G2 Nanocar, which turned out to be soluble, so we extended out the axles. So here the axles are extended out And there we could get a lot more solubilizing groups on there. And this one became soluble. And it was soluble enough for complete characterization. So that was the first soluble nanocar, so we could really characterize it well, because NMR and these tools, you need to be soluble. So that was our generation 2 nanocar. And this is probably like 2 nanometers this way and 4 nanometers this way across. And it had the wheels. Again, these are fully rotating axles. Isn't that interesting? Build cars. You know, we had made little molecules that looked like people. Maybe I'll show you that sometime. But, you know, this got more attention than that. And I realized people care more about their cars than they do about children. I mean, they just love their cars. People are fascinated with cars. And did you know that? People are really fascinated with cars. And so this got all sorts of press. And the idea was, can we put this on a surface and use an STM tip? So we worked with Professor Kelly here, and to use an STM tip, not to touch the car, but just to use an electric field to move the car along. That's the idea. And so we could see these nanocars on a surface. So you could see these 4-wheeled nanocars on the surface. And you know, sometimes you would only see 2 wheels. You wouldn't see all 4 wheels. You'd only see like 2-wheel structures. What's going on? And this like here's 2 wheels. They're the right distance apart, but where's the other 2? And what happens is sometimes these would land, instead of landing on a surface like this, they would land like this on the surface. You say, well, why doesn't it fall over? Well, there's not a whole lot of gravitational force between something that small. And so it landed like that, it just stuck like that. And so you're looking down over the surface like that, and you just see the 2 wheels coming up at you. You see what I mean? And that's what's happening. And so we could image these cars, but they weren't moving. There were too much there, and we couldn't get them to move across the surface. So we didn't want to just, you know, do static nanocars. We really wanted to show them moving. So we did another redesign. So we go through all of these synthetic steps, redesigned it, and we call this the Z nanocar. You say, well, I mean, it kind of looks like a Z a little bit, right? But not quite. But it looks a little bit like a Z. But the reason we called it a Z car is that when I was in high school, I wanted a Datsun 240Z. That was really an amazing car. I mean, it just looked really good. It didn't run well. No cars ran well back then, but it was and I really wanted a Datsun 240Z. But back in those days, high school kids didn't get whatever they wanted. And so I never got it. It was just something that I wanted. So when we got this car, I was going to call it the Z car. And so this is the Z car. And it had the 4 wheels, the 4 fullerene wheels. And it had a lot more, it wasn't so rigid. You see, this can totally spin around this chassis like this. Again, built off of these cars you've seen, these little toy cars where they can spin around like this. And that gave it a lot more mobility. And this allowed us, so we could image that 2 nanometers by 3 nanometers now. And because we built it as a rectangle and not a square, we could tell directionality. If this were built as a square, we wouldn't be able to tell directionality. What STM does, the way STM works, is it unlike AFM, which rides over the van der Waals radii of something, this is shooting electrons down at the surface. And what it's looking at is it's looking at the density of states of the molecules that are here. It's looking at the density of states that are here. And so whatever has the highest density of state is what you see. So you don't even see the chassis and the axles. You only see the fullerene wheels because that's the highest density of state. And so you see here, here's 2 wheels. Again, here's a nanocar that's landed on its side like that, and you're looking down over the top. Here's 3 wheels. You see these 3, 1, 2, 3, and the 3rd wheel is much brighter. That means you have 2 wheels down, and this now has turned 90 degrees. So there's one wheel coming up at you and the other one is down on the surface. And that's why this one is much brighter, this wheel is much brighter, because it's closer to us. And so the tunneling current is less going to that, and that shows up. So here's a car, it's facing this direction, we know because it's a rectangle and not a square, and it's going to turn and move across that surface. Here it is, moving, and right there is a collision. That was the first nano collision ever recorded. It's the first. It was the first moving nanocar ever seen. And these lighter spots are, this is a gold, and these lighter spots are a gold island that's one atom high. So you have these little islands that are just one atom up off the gold surface. Isn't that interesting? It's just one atom high gold islands. And so what you can see is you see these moving, and then people said, oh no, those aren't really rolling. Those are just sliding. Well, I said, how could they be sliding? Because the cars would move directionally. They wouldn't move sideways. They'd move directionally. They might hit something, pivot, but they're moving directionally. So we made the three-wheel version. If these were just sliding like a car on ice, this should translate as well, and it doesn't. It only spins on axis. You see what I mean? So this was a secondary verification that these were indeed rolling across the surface and not sliding like a car on ice, because the trimer only would spin about its axis. Isn't that amazing? This is like super nanotechnology. And so what we built into the Z-car was this flexibility around the axle. And that allowed us, here you could see nanocars. This is just different screenshots where the nanocar goes up and down over these one atomic step high gold islands. So what happens is you have these monster wheels, and they could climb up one atomic step high, no problem. High ground clearance, and go right on up and over to the next side. The way the STM works is it's not like it takes a picture. It scans across the surface. After it completes the whole surface, then you see the image of the whole thing. It's just scanning across the surface because there's a little tip that's getting these density of states. And what this is just different screenshots as it goes along, as it's scanning across the surface. The other thing that we could do is we could put, now, you see here, this looks like two cars kind of stacked up on top of each other, right? But it's not really two cars. It's really one car. It's really one car. And what happens is that's a tip artifact, because you can have a tip. So if you have an STM tip on a cantilever, and say you have something on a surface, this will come up and it's shooting electrons down, and this is on a cantilever that allows you to measure the deflection, and it's shooting electrons between the surface and the tip. And that's the way it works. Now, how do you get a tip that's atomically sharp? How do you get a tip that has one atom off the surface? Because you're shooting through the furthest most atom on that. And the way you get that tip is in the early days, we used to just cut with a pair of pliers a piece of wire, and that wire had one atom further out than all other atoms. You say, how can that be? Well, what do you want it to be? If you go to Mount Everest and you go to the top of the mountain, there's going to be one grain of dirt higher than every other grain of dirt, right? I mean, something has to be on the end. There's got to be something there. There's not going to be a million in a platform. There's going to be one. That's what happens. And the tunneling current varies tremendously based on distance. And so it's tunneling. But once in a while, you get a tip that looks like that. It'll have two little atoms that are both very close in distance to each other. And so that's a tip artifact. That means that particular tip had two atoms that were very close in distance. And so it was tunneling through both. So you can just neglect that tip artifact. And that's something that's known in the field. So you can put you can put the STM tip in front of this car, and the car will go toward the STM tip. It'll move because you have an electric field. And this is polarizable. It has these big molecular orbitals, and it sloshes the electron density and starts moving toward the tip. So amazing. So amazing. If this doesn't make you amazed, I don't know. I don't know if you'd ever get amazed at anything. You put the tip on the side of this thing, and the car doesn't move. What does that tell you? The car doesn't roll sideways. It only rolls forward and back. That's what that means. And so this was something nobody had ever seen this before. Imagine being the first to see this. You're like, you're amazed. You know, I go home and tell my wife, you wouldn't believe what we saw today. We saw this nanocar moving. It's amazing. And she's like, okay, take out the trash. I mean, you wonder what gets people excited. Anyway, so we made all sorts of different wheels. All sorts of different wheels. I showed you the C60. We made carbureted smaller wheels, bigger wheels, all sorts of things. So we made this one dragster. What do dragsters have? They have big wheels in the back and small wheels in the front. So we made big wheels back here, small wheels in the front, and we made a nano dragster. I mean, wouldn't you think this is fun? You get paid to do this as a graduate student. You know, go and build a dragster. And you say, well, how many of these did you make? Well, not just one. We made like 10 to the 18th of them. How do you do that? Because you make them chemically. You take advantage of Avogadro's number. We've made more nanocars in my lab than we've made more cars in my lab than all car manufacturers combined in their 100-year history. We have. We have, because we make them according to Avogadro's number. And so we have lots of these. You want a few nanocars? We can give you nanocars. We'll give you a couple of them. You won't be able to see them, but they're there. And so you see they have these wheels, the big ones on back. And so this is a step edge. So sometimes along the gold, it'll go up one step. Remember we saw those gold islands? Sometimes you have a whole step edge. So it goes up and a whole new terrace now. And so this dragster is actually straddling the terrace. So it's across a terrace. And now what happens is when this starts to move, what happens is these little wheels don't stick nearly as much to this surface as the big wheels stick. And there's a reason for that. These are all pi electron systems, and they stick with about 2 eV bond strength to the gold surface. So much so that the way we got these to move, these things moving across the surface, you can use the STM tip, or you can just heat the surface to 440 Kelvin. So you can heat it to a couple hundred degrees, 150, 180 degrees centigrade. And that's enough to get the cars moving, 200 degrees centigrade, to give it enough thermal energy. But here, the dragster, have you ever seen a dragster when it takes off really fast? What happens? The front wheels pop up, right? Right? The front wheels go up. This is exactly what happened here. The front wheels actually went up, and have you ever seen these videos of dragsters flipping over where the front wheels go up and the whole car flips? It's exactly what happened here. The wheels, it went up and flipped over to the other side. It's exactly what happened here. Isn't that amazing? It's just nanotechnology at its best. So here's the dragsters at 440K. Here's the step edge. And what happens is you heat them up, and they all start moving toward the step edge. And why do they move toward the step edge? It's because you have this terrace that's one atom step high. And right at that terrace, so you have this plane, and then you have another plane. And so you have this, you have a terrace here, and you see these atoms across this terrace. They're not bonded as well as they would like to be bonded. Because when you have a gold atom surrounded by all sorts of other gold atoms, it gets very stable. But when you have a gold atom on a surface, there's nothing else on the top of it. It's got all these orbitals sticking up, and they're not being occupied. Now you put You put some at a step edge. So not only do they not have ones on the top, they don't have ones on the side. So these orbitals, you get excess charge here. And so there's a charge buildup right at a step edge, and then as you heat this thing up, these nanocars start getting attracted to the step edge, and they go to the step edge because of the charge that builds up at a step edge on a surface. We'll pick it up from here next time. Okay, thank you. This is amazing. This is just amazing. I love this stuff. If you're enjoying this series, give us a thumbs up and click the subscribe button, and that way you'll hear when we're coming out with new videos. There are no salaried employees in this organization. All the accounting, all the legal work, that's all done by friends of mine. The only thing that I have to pay for is the production work, and if you could help us out with that, I'd appreciate it. There's a link below where you can just click on that and help us in several different ways. Thank you.